So now that we've talked about reducing and reduction operations and combining things, let's kind of zero in on the collectors part of this, which obviously relates only to the collect terminal operation. And we'll go into some more detail about the differences between non-concurrent and concurrent collectors. So recall, this is a bit of a recap. Collector is an interface whose implementations can accumulate input elements into this mutable result container. So the idea is it can be changed, it can be updated as the stream is processed. And you can determine the characteristics of a collector based on these flags that are set in the characteristics factory method, which is basically setting the metadata for a collector object. And you can make it either concurrent or non-concurrent. The distinction between concurrent and non-concurrent only applies or is only relevant for parallel streams. If you have a sequential stream, then you could have either a concurrent collector or a non-concurrent collector, and it would behave the same. You'd be kind of crazy to make a concurrent collector for a sequential stream because it adds overhead for no value whatsoever. But this discussion here only applies to parallel streams. This distinction really only matters for them. Now, just to make things even more interesting and more subtle, a non-concurrent collector can be used for either a sequential stream or a parallel stream. We saw that in the last discussions about combining results, where I showed you how non-concurrent collectors are used in parallel streams in such a way that you only do the joining of two children in a single thread, so there's no need to do the synchronization. We're going to focus on parallel streams in this lesson, so let's ignore sequential streams. So, as we mentioned before, and we'll go into more detail now, a non-concurrent collector operates by merging sub-results, and it can do this multiple times as it goes through the processing. Again, the input source is partitioned into chunks. We've talked about that before. That's what splitterators are done, or what splitterators do. Each chunk is then run in parallel in the common fork join pool, and then each chunk is collected into this intermediate mutable result container, which could be a list or a map or a set or whatnot. Different threads can operate on different instances of these intermediate results. So as you can see here, we might have a bunch of threads that are running in parallel, getting us our initial intermediate result container. And then, as we talked about before, these intermediate results are all merged together into a final mutable result container. And I should probably use the word final carefully here. It's not like Java final. It just means a single mutable result container, which is going to be the final result. Only one thread is ever used in non-concurrent collectors to merge these things together. So intermediate subresults are merged together in a single thread of control, which is good. So no need for locking. Now, the good thing about doing it this way is that this process is thread safe and order preserving if you have an order preserving collection like an array list where the order matters. However, it's costly for certain containers like maps and sets where merging things together doesn't come for free. It's very expensive. Obviously, concatenating one list at the end of another list, that's really fast, right? That doesn't take much time at all, especially if it's a linked list. Maybe a little bit longer for an array list, but a linked list, take the first chunk, you connect the second chunk by connecting the pointer, you're done. But for containers like maps and sets, there can actually be a fair amount of overhead merging all these things back together again when you're done. And we'll talk about that as we talk about the different approaches. So let's start by talking about the structure and functionality of concurrent collectors. So unlike the non-concurrent collectors, which is what we were just talking about, for concurrent collectors, there's only one result container. There's only one mutable result container at any given point in time. And the different threads that are running around doing the combining will put everything into that one container, and that will work fine as long as you follow certain important rules to make sure that that single mutable result container is properly thread safe. So that's where things get tricky. So as usual, the input source is partitioned into chunks. Each chunk runs in parallel using the fork join pool. But the difference here is that the chunks are collected into one and only one concurrent result container. So I think the best way to do this is to compare and contrast that with what you saw over here, where we had bunch of these things, right? A bunch of intermediate subresults, which then get merged together successively. Whereas for the concurrent containers, they all get stuck and accumulated into one object. Now, of course, that raises certain requirements here. All these different threads will share a single concurrent result container. So the good news is if you choose your concurrent result container properly, there's no need to merge any intermediate subresults. So it just all goes where it's going. Now, the downside with that, of course, is that the encounter order is not preserved because they just go in to whatever the container stores them, if it's a hash map or a tree map or whatnot. So you can lose encounter order. And you obviously need to have a concurrent result container that is properly synchronized. Now, why would you go to the trouble of doing this? You would go to the trouble of doing this if merging costs, the cost of merging two non-trivial containers using whatever your favorite container implementation is, a hash map or a tree set or whatnot, if the merging costs are higher than the synchronization costs. If merging costs are low, then it's probably overkill to use a concurrent result container. If merging costs are high, then it may make sense to use a concurrent result container. Now, the next question is, what are some examples of optimized concurrent containers? And so one thing to keep in mind is that not all containers are created equal. So there are some containers in Java, like hash maps, that are not designed to be concurrent at all. So they would have to be used with things like non-concurrent collectors. You'd have to do that because you map these, going to hash these things together, and they can only occur in one thread. There are also other implementations of hash map that are properly protected from multiple thread access, such as synchronized maps. But synchronized maps are really, really inefficient. We won't talk about all the reasons why they're horribly inefficient in multiple threaded programs, concurrent programs. We'll talk about that next semester. But in a nutshell, it's because they only have a single lock. And so you'll have a high degree of contention if multiple threads come along trying to add things into a synchronized map with a single lock. You'll get contention very quickly. Conversely, there's things called concurrent hash maps, which we'll again go into a lot more detail next semester. But in a nutshell, a concurrent hash map is much more clever because it has different sets of locks that cover different parts of the hash table. So as long as two values don't hash to the same bucket in the hash table, then you can have them running in parallel. So it's much, much more scalable, much more efficient. So if you choose a concurrent hash map as opposed to something mindless like a synchronized map, you're probably going to get pretty darn good behavior, and you never have to worry about merging things. You're just throwing the stuff in there directly. So that's basically the quick overview of non-concurrent versus concurrent collectors. What we will do next time is talk about, I'll show examples of how to program concurrent and non-concurrent collectors. And we'll need to be able to do this for one of the upcoming assignments.